Now that we've had an introduction to alcohols, let's take a look at the reactions that they undergo. One of the reactions that we can have for alcohols is that they can be oxidized. Remember, an oxidation means that you are increasing the number of CO bonds. And because alcohols are all starting with one CO bond, they're very readily oxidized with a variety of oxidizing agents. And one of the most common things you're going to be seeing is going from one CO bond to two CO bonds, which would give a carbonyl. So there's going to be three different types of oxidizing agents we're going to be studying. Jones, one is described as a Jones oxidation, PCC and SWERN are other oxidizing agents. And we'll start with Jones. Jones oxidation refers to either using dichromate with acid or CrO3 plus acid. What's going to happen is when we combine these, the chromium species is going to get protonated and we're going to form chromic acid. This is something that's formed in situ, and so sometimes this is just described as a chromic acid oxidation. And what happens is we take this carbon, which contains the one CO bond, that's the carbon that's going to be oxidized. And what's going to happen is we're going to replace one of the CH's with a CO, which would give this product. This would give an aldehyde. Okay, but this is not our final product because this aldehyde still has a single hydrogen on this carbon, which still can be traded for an oxygen, and this can still be oxidized. And in these oxidation conditions, the sodium dichromate oxidation conditions, the oxidation continues, so we replace the second CH bond with another CO bond. So when we start with a primary alcohol like this, a primary alcohol has two hydrogens on the carbon bearing the OH. Both of those will get replaced with carbon-oxygen bonds, and the product we're going to get is a carboxylic acid. So we get, in other words, we get complete oxidation as much as we possibly can with Jones conditions. And these are fairly harsh, strong reaction conditions. We're dealing with strongly acidic conditions, aqueous conditions, and so this is a very extreme oxidation. Let's try and predict a few products. So we have this alcohol, and we see sodium dichromate H2SO4, so this looks like Jones conditions, chromic acid, oxidation. So we find the carbon bearing the OH, and we oxidize that as much as we can. So we're going to take that carbon and turn it into a carboxylic acid. We're going to turn the CH2 into a carbonyl instead. So we get a carboxylic acid product. How about the next one? We find the carbon that's subject to oxidation right there. This carbon is the one that already has one CO bond. So when we increase the two CO bonds, let's try and look at the pattern we've had so far. How about turning this into a carboxylic acid? Something looks strange with this product, doesn't it? This is impossible, of course, because you can't have 5 bonds to carbon. So we find in this case, because this is a secondary alcohol, that's why we have we're going to see a difference in the product. Because it's a secondary alcohol, this only has one CH bond to lose, and so our product is going to just increase from one CO bond to 2 CO bonds, and our oxidation is complete. This carbon can no longer be oxidized because it doesn't have any hydrogen bonds. Remember, oxidation is an increase in CO bonds while we decrease the number of CH bonds. And this is what we're going to be seeing for alcohols. So if we have a secondary alcohol and we oxidize it with chromic acid, we're going to get a ketone product. Let's take a look at a few other oxidizing agents. One is called PCC and one is called SWERN. And these are more selective. These have milder reaction conditions. And because they're less reactive, they're going to be able to stop and do just a partial oxidation. They'll be able to stop at the aldehyde stage. So if I take my primary alcohol, again, this is the carbon that's going to be oxidized. If I use either PCC or SWERN conditions, I'm going to oxidize, go from one CO bond to 2 CO bonds, and then I'm going to stop here. It will give the aldehyde product from a primary alcohol. Okay, just a little reminder here that there's no over-oxidation with these reagents. There's no over-oxidation In other words, we don't go all the way to the carboxylic acid here. So this is going to be a big difference for chromic acid oxidation, Jones conditions, versus PCC and SWERN. For primary, we would stop here at the aldehyde. So what do PCC and SWERN represent? PCC stands for pyridinium chlorochromate. This is the structure of that reagent. This is a pyridine ring. When you have a benzene ring with a nitrogen replacing one of the carbons, we call that pyridine. And because it's protonated, we call this the pyridinium ion. And here we have chlorochromate. So you can still see the oxidizing agent here. We still have the CrO3 component, but rather than mixing it with a strong acid like H2SO4, we're going to mix it with this pyridine salt, and it's going to change the reactivity and make it be able to stop at the aldehyde. So you should get used to, if you see this reagent, you'd recognize that as an oxidizing agent. But very often you'll see it just written as PCC. It's very commonly just written as that because that's how it's known. It's an abbreviation for the reagent itself. Okay, SWERN oxidation, however, is one of our name reactions where it's named after the chemist who developed it. So you can't go up to the stockroom and say, I need some SWERN reagent. There's no such thing. Instead, it's a combination of reagents, and here's what it looks like. It's going to be a two-step process. The first step involves treatment of the alcohol with dimethyl sulfoxide, also called DMSO. And this reagent is called oxalyl chloride. So step 1, we mix DMSO and oxalyl chloride. And then step 2, we add in a base like triethylamine. And what's nice about this is when you take a look at these oxidation conditions, you see that now we have some set of reagents that no longer contain chromium, unlike the Jones and the PCC. Well, chromium is a toxic element, and so handling that is going to be hazardous, and disposing of that waste is going to be expensive and hazardous. And so chemists are continuously developing new methods that are going to be cheaper, that are going to be safer, that are going to be easier to run, easier reaction conditions, more selective, that sort of thing. So this is a really nice illustration of that. And the SWERN oxidation has a very nice mechanism too that's worth looking into, but we're not going to get into it at that point. This point we're just going to be looking at as a set of reaction conditions to use anytime we want to do one of these selective oxidations. And just a little trick, if you want to look at these reaction conditions, if I see those, how am I ever supposed to remember that these strange set of reagents represents a SWERN oxidation? Well, if you look at it very, very carefully, if you take a look at that DMSO and you think and you just kind of emphasize the sulfur in the DMSO, that might help you think of the reaction that it's a SWERN oxidation. And even with the oxalyl chloride, if you write it in just the right form, where you kind of tip in the carbonyls and spread out the chlorines, now maybe you could see the W of SWERN. And look, even in the triethylamine, we have a nitrogen for triethylamine. So when you look very closely, if you're a little bit creative, you can actually see the word SWERN. If you imagine a little ER here, you can kind of see the word SWERN buried in those reagents. So hopefully that's maybe a little trick that might help you recognize it when you see it. So we typically don't get into too much detail with the oxidation reaction mechanisms, but just to give you some idea so it's not a complete mystery what's going on, what's happening in every single one of these is whatever oxidizing agent you have is going to be reacting first with the oxygen of the alcohol and attaching some kind of leaving group to that alcohol. It's either chromium-based in the case of Jones or PCC, or sulfur-based in the case of the SWERN oxidation. But we have some kind of leaving group on the oxygen, which means that a base can come in and grab this hydrogen, move the electrons over to be a pi bond, because there's a leaving group on the oxygen that can get kicked off. So as a result, we go from a CO single bond to a carbonyl. So this is where the electrons come from. This is how a carbonyl can be generated. And what it also points out is that this hydrogen is necessary for an oxidation reaction to occur. Without that hydrogen, we would not be able to form that new CO bond. And again, if you think about an oxidation as replacing a CH bond with a CO bond, it helps reinforce the fact that you can't create a new CO bond if there's no other bond that you can lose. Okay, and most of our oxidation reactions are losing hydrogen bonds, especially all the alcohol oxidation reactions. So we go from an alcohol functional group to some kind of carbonyl containing functional group. So let's summarize what we know about these oxidizing agents, okay? The trickiest one is going to be our primary alcohol, because there's two possible products we can have for that. It has two hydrogens here on this carbon, and so an oxidation reaction can replace just one of those CH bonds, or it can replace both of those CH bonds, and so that's why we have a choice of two products we can draw. And so it's very important to choose our oxidizing agent wisely in that case. If we were to choose PCC or Swern conditions, we would take that primary alcohol and we would oxidize it partially to the aldehyde. But instead, if we were to use the harsher reaction conditions, the aqueous acid and chromium, the dichromic acid conditions, these are our Jones conditions. Our Jones oxidation, we take that carbon and we oxidize it completely. In other words, we replace both CH bonds with CO bonds, and we get the carboxylic acid. Okay, so a primary alcohol can give two possible oxidation products. A secondary alcohol, on the other hand, has just a single CH bond that it can be lost. And so any oxidizing agent, PCC or Swern conditions or Jones reaction conditions, will oxidize it up to the carbonyl, and there's no further oxidation that can take place. So secondary alcohol is going to give a ketone product regardless of which oxidizing agent we choose. Let's take a look at a tertiary alcohol. If we wanted to do an oxidation of a tertiary alcohol, again, PCC, Swern, Jones, whatever conditions that we had, any oxidizing agent. If on this carbon, if we want to increase the number of CO bonds, we can maybe turn that OH into a carbonyl. That would be a possible oxidation, but what is another problem here? This is another case where we're trying to form a new CO bond, but there's no bond that we can break. This would form a carbon with 5 bonds. So what's going to happen here? No reaction happens. There's no reaction because when we look at the carbon that we're trying to oxidize, we see that there's no hydrogen. There's no CH bond that we can lose. There's no hydrogen that we can that can be replaced, and therefore it's no reaction. So our oxidation reactions and reagents are going to, and those predict the product type problems, are going to depend on not only what oxidizing agents we use, but whether our alcohol is a primary or secondary or tertiary. Remember, the way we describe a primary alcohol means that the carbon bearing the OH is attached to just one other carbon. So because this is a primary carbon, we call this a primary alcohol. Because this is a secondary carbon, we call this a secondary alcohol. And here we have a tertiary carbon, and that's why this is described as a tertiary alcohol. Let's do one last example. How about if we were to take this polyfunctional structure and treat it with PCC? We recognize that as an oxidizing agent. So again, 3 new reagents would be a good time for some new flashcards so that you could sort the reagents out and learn to recognize them. And so we look for alcohols that we can oxidize. Here's one alcohol. This is a carbon that we can oxidize. How would you describe that alcohol? The carbon is attached to 2 other carbons, so this is a secondary alcohol. How about this alcohol down here? How would you describe this carbon? This has 1, 2, 3 carbon groups. This is a tertiary alcohol. So what's going to happen at this site with our oxidizing agent? This is going to be no reaction. So no change at this position. How about this carbon? How would you describe this alcohol? It has just 1 carbon group attached. So this is an example of a primary alcohol. In other words, a CH2OH. And what about this guy? How would you describe this functional group when you have an oxygen with a carbon on either side? This is called an ether. Okay, and that's another important thing to keep in mind is when we're learning new reagents, we always have to keep in mind which functional groups they react with. So PCC, Jones, and Swern are conditions that we're seeing react with alcohols, and so an ether is something that's also going to be no reaction. We're going to be talking later about ethers and their reactions, and we'll find that they're quite unreactive, and this is an example of that. So What we have then is our top carbon will be oxidized. We go from the alcohol to the carbonyl. So we'll make a ketone up here. This bottom carbon is still going to have an OH, an alcohol, because it's tertiary. And this carbon down here, this CH2, is now going to get turned into a carboxylic acid. And our methoxy group, our ether group, is just along for the ride, has no involvement in this oxidation reaction. So what else can we do to alcohols? Another very useful reaction that we'll employ is called the tosylation of alcohols. And let me show you an example of how this is going to look, and then we'll look at the details of the structures. If you take an alcohol and you treat it with TSCl, that stands for tosyl chloride. And what's going to happen is you're going to replace the OH group with an OTS group. Okay, and this OTS group is a good leaving group. And once we have a good leaving group, we can do all sorts of interesting reactions, just like we had a halide there. For example, we could react this with a nucleophile. The nucleophile could attack the carbon, kick off the leaving group, and we could do a substitution reaction. We could do an SN2 here. Okay, what if we tried to take this alcohol and treat it with a nucleophile? Could we do an SN2 reaction on just the alcohol? No, because this OH is not a leaving group. This is not a leaving group. It will not undergo SN2 or SN1 conditions or E1 or E2 conditions as a neutral alcohol. It is a very poor leaving group, and so this would be no reaction. So if we wanted to do a substitution reaction with an alcohol starting material, what we would do is, this is one of the strategies, is we can convert it to a tosylate, and then we would be able to do a substitution. So what does this tosyl group look like? For this first reaction, the mechanism is a little beyond our scope, but you can kind of imagine essentially the oxygen is displacing the chloride. Okay, it's not a simple SN2, but it is a substitution reaction. We're also going to lose the proton in this alcohol, so we're losing HCl in this tosylation reaction, and that explains why we need the presence of some kind of base like pyridine around, is that's going to react with the HCl as it's formed. Okay, now what does this OTS group look like? What we have here is an oxygen, and then there's a sulfur with 2 double bonds to oxygen, and a benzene ring with a methyl here. So this part from here to here represents the TS group, the tosyl group, and that stands for paratoluene sulfonyl. This is a sulfonyl group, and this phenyl group with a methyl is called toluene. So this is called a tolyl group, and para represents this relationship between the methyl and the sulfur. So this is called paratoluene sulfonyl, or just tosyl for short. And this OTS group, this is OTS. This is our great leaving group, meaning if a nucleophile were to see this molecule, it could attack the carbon and kick off this whole group. So the oxygen, along with the tosyl group, is what gets displaced. Okay, now let's take a look at the structure then of the leaving group after it leaves. What does this tosylate look like? So this is called tosylate when it leaves. The OTS is called tosylate, and this is a good leaving group. And let's examine that for a moment and make sure we understand why this is a good leaving group. We just said hydroxide is a very poor leaving group, and that's because it's a very strong base, it's very reactive, having an O-. Yet here's another structure with an O-, and we say this is a fine leaving group. So what's the difference between tosylate and hydroxide? Why is it okay for this structure to be kicked off and be on its own? Well, the key to being a good leaving group is that you are stable once you leave. And there's something about this tosylate group that makes it very, very stable. Is there any way that we can stabilize that negative charge? The fact that I have this SO double bond right next door means this negative charge, this lone pair, is allylic, so I can bring this down and move this up, and that would put the negative charge up on this top oxygen. And what do we call this when we can move electrons around, lone pairs and pi bonds? We call this resonance. And so in fact we have resonance delocalization of the oxygen up to the top oxygen. It can go down to the bottom oxygen, etc. Okay, in fact this negative charge is totally delocalized equally over all three oxygens, so it's incredibly stable. This is resonance stabilized. It's resonance stabilized. The negative charge is delocalized, highly delocalized. That's a good thing. Okay, and that's what makes it a great leaving group. That also makes it a weak base. And the same sorts of things when we talk about leaving group ability, it has to do with stability, and that also will parallel basicity. So being a great leaving group and being a weak base are kind of synonymous. So that's what the tosylate looks like, and it's going to be very useful to us when we want to turn the OH into a good leaving group. Okay, so let's try an example here. What if I had this alcohol and I wanted to convert it to this nitrile? I see that this is our new bond that's being formed here because we had 1, 2, 3 carbons to start. Those carbons are still here, so I need to form this carbon-carbon bond. Okay, let's just talk briefly about our strategy here. One of those carbons must have been a nucleophile, one of those must have been an electrophile in order for that bond to be formed. And have we ever seen cyanide, the CN group, as a reagent? We have actually seen it as cyanide anion. So this is something we should recognize as being a good nucleophile. So this guy was my nucleophile, and that means this carbon was my electrophile. Somehow we have to make it electrophilic. So can I just add sodium cyanide here and expect the substitution to occur? Is this carbon number 3, appropriately electrophilic so that we can get a substitution to occur? Well, we have the same problem we were talking about last time on the last screen, is that there's no reaction here because hydroxide is a very poor leaving group. It's unstable, it's a strong base, it's never going to be replaced in an SN2 mechanism. Okay, so how do we handle this problem? This is exactly where we would use, would be a great application of using this tosylate strategy. Rather than having an OH, I want an OTS. And once I had the OTS, now I can add in sodium cyanide, and I could expect the SN2 reaction to take place. So you have a nice primary leaving group. This would be a great SN2. Okay, and then all we need to remember what the reagents are for tosylation. We need the tosyl group. Okay, there's a chlorine on that. Tosyl chloride is what we use. That's what the oxygen is going to be replacing on the sulfur. And then we always do need a base in here as well to get rid of that proton. And so you could just write base, but most often we use pyridine. So that's nice to be familiar with those reagents and be able to see them being used in tandem. That's probably how you'll be seeing it down the line. Okay, we just talked about, we've already talked about oxidations of alcohols. How can we increase the number of CO bonds? We can also do reductions of alcohols. So a reduction means we're going to decrease the number of CO bonds while increasing the number of CH bonds. That's the opposite of an oxidation. And so an alcohol has just one CO bond. So in order to reduce it, you'd be going to replacing it with a hydrogen. So you'd be going from an alcohol to an alkane. We would describe that as a reduction of an alcohol. And there's a few strategies we can do for this. One of them is via an SN2 mechanism with hydride. Hydride is H-. And if we had a source of hydride, then it can do an SN2 mechanism. But what's the problem with just using the alcohol? The source of hydride we had that was nucleophilic was something like lithium aluminum hydride. Lithium aluminum hydride, LiAlH4. That was a source of hydride. What would happen if I mixed an alcohol and lithium aluminum hydride? Well, I wouldn't expect to do an SN2 mechanism because, once again, my OH is a poor leaving group. But in this case, it's not that there's no reaction, because the hydride, just like a Grignard, is an extremely strong base, and the alcohols, remember, have a very acidic proton. That's one of the properties of alcohols. So in fact, this would react to give an O-. It would deprotonate, and you would get some hydrogen gas being formed, and you would form the lithium salt here, or the aluminum salt of the O- of the oxygen. And so this is fine if you want to deprotonate. You could use LAH to deprotonate an alcohol, but you couldn't use it to do a substitution. So instead, here's another case where if we instead made the tosylate, tosyl chloride and pyridine, replaces the OH with an OTS. Now that we have a good leaving group, LAH, lithium aluminum hydride, can do an SN2. This is a great nucleophile. Remember, we put little quotes around it because it is always coordinated with the aluminum. That's the nucleophilic hydride that we have, and it will, in fact, do an SN2. And that would be a way of replacing a leaving group with a hydrogen, in this case, a tosylate with a hydrogen. So overall, our transformation has been to reduce the alcohol. Okay, just a little note here. Another source of hydride we've seen, especially with alcohols, is sodium hydride. We use this as a base, and in general, because this is ionic, because this is more reactive, this prefers to act as a base rather than a nucleophile. Okay, so when you're thinking hydride, that's a good distinction to make, is that when you want a nucleophilic hydride, we use sodium borohydride or lithium aluminum hydride, and NaH you should consider just as a base. Anytime we want to deprotonate something, NaH would be a good choice there. Okay, another strategy is to think about, maybe if we do a retrosynthesis here, and we consider what reactions have we ever seen that give alkanes as products. That's kind of a strange reaction because there's no functional groups here. There's nothing left. Okay, well, what if we had an alkene in this position? Have we ever seen the conversion of an alkene to an alkane? Looks like we've broken the pi bond. We've added something to each carbon. What did we add? We added a hydrogen, and of course there's a hydrogen here too. This was a CH2, and now it's a CH3. So we could do catalytic hydrogenation. If we had an alkene, we could do a catalytic hydrogenation to give an alkane product. And what's nice about this is we've also seen alkenes as something that can be prepared from alcohols. Now, what does that reaction look like? What reagents will cause that transformation? We are doing an elimination. We're eliminating an OH, but we're also eliminating a hydrogen on the neighboring carbon, the beta carbon. So we're losing a molecule of water. We call that dehydration. And what reaction conditions do we need to dehydrate an alcohol? It's going to be some heat, very strong acid. So something like H2SO4, heat, strong, concentrated acid is what we need to do a dehydration. And so this would be a way of forming an alkene. Now remember, dehydration, we can have our alkenes move around. We could have we could have hydride shifts and such to get more stable carbocations. And so it's possible that our double bond might move around, but that's okay in this case because hydrogenation is going to get rid of the double bond in the end anyway. So we don't care so much where the double bond ends up here, but we do want to make sure that our carbocation is not something that can have a carbon chain rearrangement, because then that is not going to give us the alkane structure that matches the alcohol structure. So the dehydration is only going to work if there's no rearrangement of the carbon frame, of the carbon skeleton. Okay, and if that's the case, then this is another great way to do the transformation is dehydration followed by reduction. Okay, so as you can see, reduction is not going to be something, there's no one magic reagent that's going to reduce an OH and replace with a hydrogen. We have to do some kind of multi-step transformation, either turning it into a good leaving group or getting rid of the oxygen first as a molecule of water, and then doing a complete reduction of both of these carbons via catalytic hydrogenation. Another handy thing we could do with alcohols is convert them to alkyl halides. So this conversion going from an ROH to an RX looks like another substitution that we're trying to do here. We're trying to substitute an OH with a halogen, but as we've talked about in the last few slides, in order to do a substitution, the key is we need to make the OH a good leaving group. Otherwise, we can't do a substitution. So one strategy that we've already seen is to do the tosylate. That strategy will work here as well. So if I wanted to replace the OH with a bromide, with a bromine, I could use tosyl chloride and pyridine to make the tosylate. And then I can use sodium bromide, NaBr minus, NaBr to give me a bromide nucleophile, and we can do an SN2 here. Okay, so that would be a great way to do a substitution. That certainly works as a strategy. And another reaction you might recall from back when we were learning about SN1 and SN2 substitutions and being introduced to those, we learned another way to make an OH a good leaving group is to use a strong acid. So something like HBr or HCl. Sometimes instead of just HCl, you might see some zinc chloride thrown in as a catalyst. HCl is a little less reactive, so we need that to speed things along. But the concept is the same in either case. What we're doing is taking the alcohol and not just treating it with bromide. If we were to try and do this and sodium bromide, that would be no reaction because we don't have a leaving group. But instead, if we react with HBr, then that's going to be a source of H plus and Br minus. Okay, remember this is a very strong acid. So let's, and we can get a substitution take place. So let's think about a mechanism here. What do we know about HBr or HCl? A strong, either of those, they're very strong acids. So the very first step, once you recognize that you have strongly acidic reaction conditions, the first step of your mechanism is going to be to protonate something with that strong acid, let it donate a proton to anything that can take it, and the alcohol can certainly accept a proton here. So we can protonate the alcohol. And how does that help us move forward in our substitution? Because protonating the alcohol is another way of making a good leaving group. We talked about how the tosylate is such a good leaving group because the O- is resonance stabilized. What would your leaving group be in this case? It would be water. Very stable molecule. So now we can have our substitution. The substitution or mechanism here, let me make a note, can be either SN1 or SN2. So once we make a good leaving group, now we can either have that leaving group leave to give a carbocation, or we could have the nucleophile kick out the leaving group with a backside attack. Because this is secondary, we probably will get a mixture of both. So remember SN1 or SN2. In this case, we'd probably get both happening to some extent because it's secondary and they're both allowed. But we can most definitely do our substitution. Okay, the other product here is water. And water, of course, is extremely stable. And that makes him both a weak base and a good leaving group. So that's what makes this substitution reaction on an alcohol possible, is we protonated it first to enable it to leave as water. Okay, now a few things about when can we use HBr and HCl to do this substitution. Okay, one thing is that the conditions favor carbocation. These are acidic conditions, strongly acidic conditions, and those sorts of conditions always favor carbocations. So that means the SN1 is going to be favored, but that also means we can maybe have some elimination reactions, some E1 products. We can most definitely rearrange certain carbocations. Tertiary is going to be the best conditions to do this reaction because it gives such a good gives a stable carbocation, so that's going to be a very fast reaction. So using HCl or HBr to make the chloride or the bromide is not going to be suitable in every case of an alcohol. Okay. In addition, the reagent HBr or HCl can react with other functional groups besides just an alcohol. So, for example, we've seen reactions where this adds across a pi bond. If you had any alkenes in the structure or alkynes, they would certainly react under these conditions. We'll see that ethers also react with these halo acids, so that might be a problem, and so on. Okay, so these, although this is a reagents that we're familiar with and we've seen before being used, we're going to learn that these are not always the best reagents to use. And so next we're going to learn about some reagents that might be a little more suitable to do this transformation. Okay, and this involves some new reagents for us, and what each of these do is they both provide the leaving group and they provide a nucleophile all in one pot. So all at once we add this one reagent and it both makes the good leaving group and it replaces that leaving group. So unlike the tosylation, which is a two-step process, you have to make the tosylate and then you displace it. And unlike the HBr or HCl, where you have these strongly acidic conditions that do some other side reactions, these reagents simply take what used to be an OH, and if you have SOCl2, it's called thionyl chloride, it's going to replace that OH with a chlorine. And so there's no chance for rearrangement of carbocations, and so on. To make the bromide, we're going to use PBr3, that's called phosphorus tribromide, and that would be a great way to make bromides, alkobromines. And then if you want to do the iodine, we do another phosphorus reagent, but we just kind of make this in situ. We just combine phosphorus and iodine, and it takes the OH and replaces it with the iodide. So you can see we have some phosphorus reagents, or SOCl2. You might ask, well, is there a chlorine version of this phosphorus? Sure. There's also PCl3, there's PCl5, there are all sorts of reagents that are similar to this. Again, wide variety, but what we try and do when we're introducing a new subject like this is we try and give one representative compound or reagent, and these are the ones that you'll probably see most likely in an organic textbook, so that's why I stuck with these. Okay, and also different texts emphasize or de-emphasize the mechanism of these reactions, of these transformations, because again, they're usually a little beyond the scope of an introductory course. But let me just show you some brief information about the mechanisms. SOCl2 has this structure when you react it with the alcohol. And again, this reaction is also going to be done in the presence of some base because we have to lose HCl. But the oxygen replaces one of the chlorines. We get this kind of intermediate. And then what happens is the sulfur actually delivers this chlorine internally to the carbon and kicks the leaving group off. Okay, so this is a good leaving group. So the SOCl2, kind of like the tosylate, makes this sulfonyl kind of leaving group, but it also has a chlorine on here which will replace that leaving group as it leaves. It gets an internal delivery. Okay, so internal attack of the nucleophile, and what actually happens with the stereochemistry is we get retention of stereochemistry. So if this was an alcohol, let me put on an R group here so that we can have a chiral center. If this alcohol was a wedge, and this sulfonyl intermediate would still be a wedge because all we did was react this oxygen, it turns out that the chlorine is still going to be a wedge. Okay, now again, the stereochemistry is usually not a real big issue here, but this is generally the mechanism we're seeing, and typically we see a retention of stereochemistry if we have that. Okay, if you have a phosphorus type reagent, again, the first thing that happens is the phosphorus is going to combine with the oxygen. It's going to react with the oxygen to make a good leaving group. So this is another good leaving group. And then it's also going to be the source of bromide, we displaced the bromide from this phosphorus, so the bromide is still around. So after we make that good leaving group, we're going to get displacement of the leaving group. This mechanism looks like backside attack because from an external nucleophile, that's what we have here. We have an SN2. So what kind of stereochemistry do we expect in that sort of substitution? Backside attack gives us inversion of stereochemistry. So if we adjust this to be, again, a chiral alcohol, and we think about the stereochemistry, if we had this OH group as a wedge, it would still be a wedge here because we haven't had any chemistry at this carbon. But at this point, now if the leaving group was a wedge, the nucleophile would have to come from behind that. And so our leaving group, our halide now, the incoming nucleophile, is going to be in the opposite stereochemistry. It's going to be a dash instead. So these reagents of SOCl2, PBr3, and phosphorus and iodine are really used more routinely in the conversion of going from an alcohol to an alkyl halide because it avoids some of the pitfalls that we see with some of the other options that we have. Okay, let's see an example of a transformation. And this is not a transformation we've seen before, but it is a reaction of an alcohol. Let's see if we can figure out how to go about this to convert the alcohol to this. This looks like an organolithium. Remember we saw these structures RLI. We have some carbon group with a lithium attached. And this is related to the Grignard reagents we've seen. This is an example of an organometallic. And anytime you want to make an organometallic reagent, and we ask ourselves, or we do a retrosynthesis, and we say, what starting material do I need? What functional group do you have in order to create an organometallic reagent? Well, you need some kind of halide here. And in this case, because that halogen gets replaced by the lithium, it doesn't matter what halide you have. With the Grignard, you still see the bromine or the iodine or the chlorine here, so you know which halide you need. Here it could be anyone you want. So this could be chlorine or bromine or iodine. And we have those. We've seen that transformation, conversion of alcohols to alkyl halides is definitely something we can accomplish with some kind of synthesis. So let's think about possibility. How about if we used, let's say we wanted to make the bromide. That's not a bench ring. Let's say we wanted to make the bromide. How about I just put this as a phenyl group? That'd save us a little time. If I want to make the bromide, how can I do that? Well, what if I used HBr? HBr is one option. It will protonate the OH and make it a good leaving group, and the bromide can replace it. Would this be a good substrate to do HBr? Well, I mean, it certainly could work, but because this favors carbocation, and because we are right next to a benzylic position, which would be a very good carbocation, there's a chance that we could get some rearrangement. There's a chance that we could get some of this bromide mixed in with this bromide, and we want to avoid rearrangements anytime we can. Of course, I skipped right over the fact, we already pointed out a few times, I can't just use sodium bromide. I can't just try and do an SN2 right away because that wouldn't work either. I don't have a good leaving group. So how do I make the OH a good leaving group? Well, I could make it the tosylate. I can make a tosylate and convert that to the bromine, to the bromide. So that's good. What would be my reaction conditions to make the tosylate? It's TSCl and pyridine. And then to make the bromide, now I could use sodium bromide, NaBr, because I have a good leaving group here. Okay, so that two-step procedure would be okay. What's another process I can use? I can just take my alcohol and just in one step, I can add PBr3. So that would do the same transformation. There's no chance of rearrangement there. So that would probably be a better choice in the laboratory. Although this transformation is acceptable too. Okay, once I have the bromide, either via the tosylate or via PBr3, how do I go from the alkyl halide to the organolithium? Well, the way we make our organometallic reagents is we simply add in the metal, and that will react with the halide. So in this case, we just use lithium metal. You can write lithium 0 if you want, or you could just say lithium by itself. It's not the cation, it's just lithium metal. And remember, lithium does an exchange, a halogen metal exchange, and so that would be a way that we could form this, this organolithium. So we've seen a nice overview of the various reactions that alcohols can undergo. A lot of new reagents on this topic. So again, keep up with those flashcards so that you can stay on top of the reagents and what kind of products you can expect for those reactions. Also, a few mechanisms in this unit, but not quite as much as we have for our new reagents.